Hi, welcome back. So in the second video of the series, we'll be looking at the requirements for the flow at the evaporators and further motivate why the two-packle is designed as it is and giving it a closer look. We'll be looking particularly at the detector side. We will also do a quick comparison between the Atlas and CMS two-packle plants. Finally, I'll give an example of how cooling is distributed in one of the detectors. And the detector that I will be giving an example of is Atlas ITK or Atlas Inner Tracker Detector. So I think to understand why the two-packle is designed as it is important to first understand the flow along the evaporator or detector. All the two-packle is designed so that we have the proper flow requirements along the evaporator. So as discussed previously, the evaporator is a pipe carrying CO2 refrigerant inside the evaporator. Along this pipe, silicon sensors are glued, and these silicon sensors measures the trajectories of charged particles. To shield them from the high radiation and to protect them, we need to cool them down to temperatures along minus 40 degrees Celsius. So in this diagram here, we're drawing an example of what the temperature profile might look like along the evaporator. So say we enter the evaporator in liquid CO2, and right after the beginning of the first silicon sensor, the heat from the silicon sensor is absorbed by the refrigerant. As a result, the liquid CO2 increases in temperature until it reaches the boiling point. Right after the boiling point, we are boiling or in two-phase. And it's important to be in two-phase along the evaporator. One, because of its isothermal properties, that is, the temperature difference between the first and last silicon sensor is minimal. And two, because two-phase has a much higher heat transfer coefficient compared to liquid. Heat transfer coefficient can be thought as the efficiency at which heat from the silicon sensor is absorbed by the refrigerant. Also, I wanted to add that the reason why two-phase is actually decreasing in temperature is because as the refrigerant is flowing along the evaporator, it's dropping in pressure, and the boiling point decreases with decreasing pressure. So on this slide, we will discuss another requirement for flow of the evaporators, which is the capillaries. So the capillaries have two main functions in the detector. The first being to distribute the flow to the tight areas in the evaporators, and the second as a fail-safe to protect evaporators in case subsequent evaporators break, which we'll be discussing shortly. So here I drew the beam path of which the protons collide, and the evaporators form a cylinder along this beam path in order to measure trajectories of charged particles in all directions. So the evaporators might be a semicircle, and on the other hand, there's another semicircle on the other side to close the loop. So the flow is usually distributed in parallel to multiple evaporators. So in this first diagram, we have no capillaries, and we're having 12 grams per second of refrigerant. If the evaporators are calibrated, then we have the same flow rate across all evaporators. However, if an evaporator's silicon sensors break, then there is no longer heat transferred from the silicon sensors to the evaporator. As a result, the refrigerant will no longer boil and will remain liquid. Now, in contrast to temperature drops, in two-phase, the pressure drop at same mass flow rates is much higher than liquid. This is because at the same mass flow rates, two-phase is flowing at higher flow speeds, and as a result, has higher frictional pressure drops. So, in this loop, we are liquid, and as a result, the pressure drop is lower. The flow will redistribute, and of course I'm exaggerating, but it might redistribute as such. These evaporators will no longer be cooled efficiently to minus 40, and these temperatures will rise. And the result of low flow speeds, these further evaporators would break as a consequence of the single evaporator breaking. However, if we introduce capillaries, we're increasing the total pressure drop along the evaporator. As a result, the failure of one evaporator would no longer be as dramatic. So now say that this evaporator breaks. The flow will still increase in this loop, but not as dramatically. As a result, these silicon sensors will still be able to cool to minus 40 degrees Celsius. So looking at this pressure and enthalpy diagram on the left, which we drew in the last video, after the chiller, we're at 0.1. And in theory, we could go from 0.1 to 0.4. However, as we saw, this is very sensitive to a single evaporator failing. As a result, we increase the total pressure of the refrigerant and then drop the pressure with the capillary. So now we'll be giving it a closer look into two-packer. So these components, which I've circled, we've already seen before. Now we're introducing primarily the warm nose heat exchanger and the detector flex line. So the warm nose heat exchanger adds heat or enthalpy to the refrigerant before it enters the detector. So on this slide, I will describe why the warm nose is implemented. So with the warm nose off, if the geometry is not calibrated properly, the refrigerant will enter in liquid at the evaporator. And then right after the heating, it will increase in temperature and then boil. However, the warm nose increases enthalpy before the capillary, and as a result, the refrigerant enters already boiling or already in two-phase. Therefore, the temperature across the evaporators is much more consistent compared to the warm nose off. Also, in some cases, we might have superheating. Superheating is when liquid increases its temperature above its boiling point. This causes high temperature spikes, and the warm nose would eliminate these temperature spikes. Temperature spikes are bad for the silicon sensors since they might break. So as I said in the last slide, now we'll introduce these components. So once again, the service cavern is separated by the wall to the experimental cavern. The service cavern contains most electronic components, and it is separated because of the high radiation doses in the experimental cavern. Most components in the experimental cavern are passive. However, these components have a much lower radiation dose compared to the inner detector, and thus are safe. The warm nose heat exchanger is a heat exchanger which warms liquid CO2 right before the detector. It does so by a secondary flow of warm CO2. So the warm CO2 is split from the main transfer line and warmed up using this warm nose heater. It is then boiled or in two-phase. This warm back pressure regulator regulates the temperature of the secondary flow because it's in two-phase. So the temperature or the boiling point can be regulated based on pressure. Then the detector flex line routes the main flow to the inner detector. So this is another concentric transfer line like the main transfer line. And there's warm CO2 warming cold CO2 in. The detector flex line is composed of a concentric liquid line surrounded by a two-phase outlet. So it's two lines, one within the other. The flex line is also insulated by a vacuum jacket. So here we have vacuum, here we have two-phase, and inside we have liquid. So now let's walk along the pressure and enthalpy diagram for the Atlas detector. So once again, we'll start the pressure and enthalpy diagram at 0.1, where the fluid has just been condensed by the main chiller. So the pump increases the pressure of the refrigerant, and as a result of its imperfection, also increases its enthalpy. Then the fluid passes through the main transfer line and is transported inside the experimental cavern. The outgoing CO2 is going to warm up the incoming CO2. So as a result, the points 2 to 3 will be shifted to the right. This increase in enthalpy will be the same decrease in enthalpy from point 8 to point 9. The detector flex line will have the same exact purpose as the main transfer line. Thus, point 3 will be shifted to the right to point 4, and point 7 to the left to point 8. The warm nose heat exchanger will cause a further increase in enthalpy to the refrigerant. The warm CO2 is split from the main transfer line and is heating up this incoming CO2 here. Then the capillary will cause a decrease in pressure from point 5 to 6. From point 6 to 7, we enter inside the evaporator where the refrigerant is boiling, or in 2 phase. Then, skipping back to point 9, the fluid is condensed by the main chiller and shifted to the left back to our starting point. So with the warm nose heat exchanger, we are entering the evaporator at around 3% vapor quality and exiting the evaporator at around 30% vapor quality. This is because we want to avoid boiling the CO2 to higher vapor qualities. Because if we boil too much and we reach gas, the heat transfer coefficient is very poor and the silicon sensors will break. So our safety is 30% vapor quality at the outlet of the evaporator. So now we'll look at the differences between Atlas and CMS. Atlas, as we saw previously, has a warm nose heat exchanger to increase the enthalpy before the detector. On the other hand, CMS places a small electric heater before the inlet of the evaporator. There's pros and cons to either side. While CMS is a simple solution and occupies little detector volume, its electric heater is sensitive to high radiation doses inside the detector. On the other hand, the warm nose heat exchanger is passive, however, occupies a larger detector volume inside the detector. So finally, let's look at an example of how the cooling is distributed in one of the detectors. The example we'll be using is Atlas inner detector. So the concentric transfer line takes the CO2 from the service cavern all the way to the experimental cavern. First, we encounter an inlet manifold, and the inlet manifold takes to the manifold box number 2, which then takes to the manifold box 1. In between inlet and manifold boxes, there's large distances covered. The manifold box 1 takes it to the inner detector through the use of the flex lines, which are concentric as we discussed previously. After the flex lines, the flow encounters the warm nose heat exchangers and finally to the detector loop manifold. In this manifold, there's 6 evaporators. The warm nose heat exchangers are supplied by the warm nose box, which steals flow from the inlet manifold. These are on series. Finally, all the 2-phase outlet flow flows through the outlet manifold, which then passes in the concentric transfer line. So this concludes the second video in which we took a deeper dive into 2-PACO and how cooling is distributed in Atlas.